All right, so what if you want to predict the weather without thinking about potential vorticity? Right? Well, it's still possible. You can still talk about development, time development. So development of low pressure centers, for example. You can talk about that in the Quasi Geostrophic framework without going through this forward step inversion process with the potential vorticity. You can just say, well, here is our development equation for the potential vorticity, but we haven't used the words potential vorticity, we've just written it down, okay? We can rearrange it, okay? So let's just assume all the functions are well behaved, differentiable, etc. We can swap over the order of the derivatives. So instead of having d by dt of this great big function of psi, we just have a function of d psi by dt. And we equate that, we just put this on the other side, do the same thing with that. We have two terms, right? So what is it that determines the tendency of the stream function? And by implication, the pressure. So we're looking for pressure development here. Tendencies of the stream function will tell you if that's negative, then you're developing a low pressure. So that will be determined by what? This is the minus v dot grad of the absolute vorticity. Right? So vorticity advection. Vorticity advection will influence pressure development. Okay? And this one here, d by dz, v dot grad of d psi by dz. So this is the vertical gradient of an advection. Well, it's like the density. This is the density. So this is related to the vertical gradient, actually, of the horizontal temperature advection, the way it's normally thought of. Right? Except you've got this, still got this operator to worry about, this elliptic operator in front of your tendency term. So what we have to do is assume that the functional form of this is fairly simple. Okay, so if we just say that it's a wave-like in x and y, and it's a simple mode in the vertical, which changes sign once in the vertical, then you can say that the effect of this operator on that simple wave-like structure will be just to multiply it by a constant, okay, involving the wave numbers. And so it's just a change of sign. So then you can, if this is true, you can just say that your development is proportional to, we change the sign of the right-hand side terms, but they're still related to the vorticity advection and the vertical gradient of the temperature advection. So let's just start by looking at the vorticity advection. Right? Advection of absolute vorticity. We're proportional to v dot grad of del squared psi plus f. Well, let's just think about the relative vorticity part first. And we say that relative vorticity, if it's a wave-like structure, then it's going to be proportional to psi. And, well, you have a, here's an illustration in which you have a wave-type structure in the flow. And so in this part of the wave, in the crest here, the relative vorticity is negative, and in this part it's positive. And if the flow is going that way, then you have advection of negative relative vorticity, okay? So minus v dot grad of the vorticity is negative, okay? And if that's the case, then that means that d psi by dt will be negative. Or conversely, if it's positive, that means d psi by dt will be positive, which will be the case here in this part of the wave. If you have a ridge and then a trough, you'll have development downstream of the ridge and the trough in such a way as the relative vorticity part of this tendency will cause the whole structure to propagate in the same direction as the flow. Okay? You have to think long and hard about the signs in this, but that is the conclusion. The other part, the planetary vorticity part, planetary vorticity Coriolis parameter, it's just that you have, if you have flow from the north here, then you're bringing down larger values of f, so you've got positive advection of vorticity, and then flow from the south, negative advection. So you're bringing down flow with more vorticity or taking it north with less vorticity. So that will have the opposite effect, and it will cause the wave to propagate in the other direction. So this competition for the development between this is the Rossby wave term, and this is the more synoptic scale term. which is kind of two different terms which will both influence the way in which the weather will develop. And how about the other term which can affect the development? The vertical gradient of the temperature advection. So you have this rate of change of the stream function, and by implication the pressure, which is proportional to the vertical gradient of this thing, which is related to the advection of temperature. And basically, I mean, you have to, as I say, you have to scratch your head and look at this a long time. I can't do it for you. Think about what is the variation in the vertical of this advection, okay? So here's an example where you have Vg.grad T is greater than naught here. You've got flow coming in from the west, and you've got cold air here, warm air here. So you've got cold advection. Gradient of temperature is positive, all right? So cold advection. But it's decreasing with height, and that will be associated with a negative tendency in the pressure, so you'll have development of low pressure here. Here you have the opposite, you've got warm advection, which is also decreasing with height, so that part is the same. So it'll be the opposite sign, and you'll have development of high pressure, okay? So you'll have a trough developing downstream here, a ridge developing downstream here. So that's the prognostic part, okay? That's how to predict the weather with the quasi geostrophic arguments. It's also possible to do diagnostics with the quasi geostrophic set, and this is very useful because often when you're doing weather analysis, you want to know where the vertical velocity is. Where do we really have upward motion? Because that's important for development again. So you can deduce the vertical velocity by integrating dw by dz in the vertical, and this is given simply by continuity. That's mathematically sound, but the trouble with that is that it's ill-conditioned in a way because this horizontal divergence is extremely difficult to be accurate with. It's a small difference between large terms, okay? du by dx and dv by dy will have a large cancellation between them, right? So it's not a very accurate way of finding the vertical velocity with real data sets. Quasi-geostrophic system to the rescue. From the quasi-geostrophic set, we have the vertical velocity is equal to this. The Berger number times d by dt of dp by dz plus v dot grad dp by dz. Now, we didn't do that in class today. That's on the blue pages, all right? But I don't have time to do all that, right? So that comes from a continually stratified version of QG theory. Well, it's got these two terms, right? And the game we tend to play is that we take something and we try and find another equation and manipulate it to produce something similar, and then we eliminate lots of terms, we end up with something useful, right? So here is the vorticity equation, and we take the Laplacian of this equation and compare it with the vorticity equation and mix it all up, and you end up with this, right? What we have here is some elliptic operator again times the vertical velocity is equal to these two terms. So something related to the vertical velocity, and again, if the vertical velocity has some simple trigonometric dependence with height, this will become a constant, is equal to these two things. And this is the vertical gradient of the vorticity advection. And this is, well, the Laplacian of the temperature advection. So it's the other way around to before. Before we had the vorticity advection and the vertical gradient of the temperature advection. Now we've got the vertical gradient of the vorticity advection and the temperature advection. Okay? And those two things will contribute to finding out what the vertical velocity is. The first term, the vertical velocity is proportional to, the elliptic operator has just switched the sign here. Vertical velocity is proportional to minus d by dz of v dot grad absolute vorticity. So it's proportional to the rate of increase with height of the positive vorticity advection. Sounds like a mouthful of things to say, doesn't it? And this is what it's like. This is synoptic meteorology. Synoptic meteorologists talk in multiple derivatives, right? So this is the vertical gradient of something which is the velocity multiplied by the horizontal gradient of something which is itself constructed of gradients, right? And yeah, so the vertical velocity is proportional to the rate of increase with height of positive vorticity advection. Over the low, we have vorticity increasing. If you have vorticity increasing, then you have a negative stream function tendency from the previous thing we were talking about with the tendencies, right? So the geopotential surface is falling, the thickness is getting less, so we have cooling, and thus we have upward motion to balance the cooling. It all hangs together, right? All the different aspects of the dynamics are consistent, and there are many ways to describe how this is true, that this fact that the vertical velocity is related to this term in the vorticity advection. Second term, temperature advection, and it's just the temperature advection, it's not the vertical gradient this time. The vertical velocity depends on warm advection. So we have upward motion wherever we have warm advection, right? And downward motion where we have cold advection. It all gets very complicated. You have to sit there and scratch your head a long time looking at these equations and making sure you've got the sign right, because if you've got the sign wrong, you've got it completely wrong, right? Here's a summary. For the tendency equation, the fall or rise of geopotential is proportional to the positive or negative vorticity advection, or the rate of decrease with height of the cold or warm advection. And so that for the vertical velocity, for diagnosing the vertical velocity, rising or sinking motion is proportional to the rate of increase with height of the positive or the negative vorticity advection, right? Or warm or cold advection. Right? And that, I think, is it for today. Yep. So now you know, right? If you had doubts before about what quasi-geostrophic theory is, now you've just had a whole load of it rammed down your throats, and it's going to take you a while to digest all that. But that was necessary, and the things we're going to do from now on are going to be much more applied towards real interesting phenomena. This is just a grounding, okay? So next week, we'll talk about Rossby waves, okay? So don't forget to like and subscribe.